Physics Lab 5 Slinky. The goal of this lab was to determine the effects of gravity and drag on the motion of a slinky and use this to computationally predict the motion of a slinky. This lab used the Newton's second law with the position update and velocity update formula, the weight force and the drag force. This was the model of the physics principles where the tension was pointing upwards, gravity was pointing downwards, and this was when it was at equilibrium, so the net force was equal to 0, and then eventually it moved downwards, so the net force was downwards. And I also considered the drag force pointing up. The main result was that the tracker analysis spring moved down at a faster rate than the computational model. So these were the system and the surroundings. The system was just mainly the spring. This was the frames per second, the mass of the spring, the initial position and final position. And this is how the video is analyzed through tracker analysis. So these are the initial conditions put into the computational model with the gravitational constant, the delta t, initial position and velocity, and the mass of the ball. And it also included the proportionality constant for the drag force. This was the first while loop, considering the weight and the tension force initially before 0.52 seconds, and it updated the position and velocity. This was the second while loop, after 0.52 seconds till the last timestamp in the video, which considered the weight force and the drag force. So it overcame the tension force, and then there was just weight and drag. And it updated the position and velocity in the code. So comparing the model versus the observed comparison, they didn't really line up on the graph. This was the tracker analysis, and it moved down at a very fast rate. Eventually, at this part, it only included the tension and gravitational, while here it included the gravitational and drag force. So it moved down at a faster rate. While the computational didn't really move a lot, it did move a little towards the end, but the computational dips only slightly, meaning there was a possible lower drag resistance in real life, and the variance is also due to error in tracking points on tracker analysis or error in calibration. So why does the bottom of the slinky initially remain stationary? It remains stationary since the tension force of the slinky is equal to the force of gravity. The bottom of the slinky is in static equilibrium because the two forces acting on it, itself and gravity, are opposite and equal. Thank you.